Hey guys, this video is going to be a summary of Chapter 10, specifically Section 10.1 and 10.2, which is what we've covered this year. And I let Mrs. Gasello and Mr. Havens take the lead in this chapter for you guys because I hadn't taught it before in the Algebra 2 curriculum, and I wanted to make sure, especially with these weird circumstances, that you were really getting efficient information to you. And I was trying to be there to help you through with questions, and I was like a student watching their videos as well. So this is my chance to just kind of summarize for you the main points in Chapter 10. If you feel like you need it, please watch this. I'm going to cover the difference between arithmetic and geometric series. I'm going to cover finding the sums using formulas, summation notation, and I'm also going to include 4 questions from that are very similar to closure problems that I think you really need to know in order to be successful for your 2 tests this week. So, first of all, Chapter 10 is about series. And remember, series is just the sum of a sequence of numbers. And a sequence of numbers, remember, is just an ordered list of numbers. Okay? There's 2 types we talked about in this chapter. One is arithmetic and the other one is geometric. And coming from Algebra 1, hopefully you remember, arithmetic just means when you're either adding or subtracting the same number from one term to the next. So here you can see we're adding 2 each time along the way, making this an arithmetic series. Here we're subtracting 2 each time, again, making it an arithmetic series. Arithmetic series can be written, you can write the rules of arithmetic series using linear equations, and I'm going to talk about using first term form. So the first term is 2. We're adding 2 every time, and we're going to start with n minus 1. Meaning, if I put a 1 in for n, this is my first term. 1 minus 1 is 0. 0 times 2 is 0, plus 2 is 2. That's my first term. If I plugged in 3, 3 minus 1 is 2. 2 times 2 is 4. 4 plus 2 is 6. I'm getting the correct terms. Okay? Geometric series, on the other hand, is when you have a common ratio. So really you're seeing things that are either multiplying or dividing by the same number from each term to term. So here you can see we're multiplying by 2 each time. Here we're dividing by 2, but remember we want to talk about that like multiplication. So we're really multiplying by either 1/2 or 0.5. Clearly those are the same things. Okay? If I want to write a rule for a geometric series, then I need to use an exponential equation. Okay, so again, I'm using first term form. My first term, actually, I'm going to do this one down here. My first term is 20. Okay, what am I multiplying by? That's the 1/2. And again, I'm doing n minus 1. So this is my first term. If I plug in a 1 for n, I will get 20. If I plug in a 3 for n, I will get 5. Okay? Next, we have learned 3 different sum formulas. Okay, actually I'm just going to do this. 3 different sum formulas that we use throughout this chapter. I'm just going to play musical boards for you right now. And so the very first one, the sum of some number of terms is equal to n, that's the number of terms, times the first plus the last term divided by 2. Now, anytime you have an n, it means that we have an ending of our series, meaning we have to know the number of terms. It cannot go on and on forever if we're looking for an n. Okay? First and last, this of course is arithmetic. And again, because it does have an n number of terms, it is a finite series. Finite means it has an end. This has an end. Okay? The last 2 are both geometric. One clue knowing why they're geometric is these r's represent the common ratio. So the r for this one would be 2. The r for this one would be 1/2. Okay? Now, in the chapter, you sometimes saw r to the n minus 1, and sometimes you saw 1 minus r to the n. And if you saw 1 minus r to the n, you also saw 1 minus r. Either formula is correct. They will both get you the same answer. It's kind of like when you're trying to find the slope between 2 ordered pairs. If you do y2 minus y1 over x2 minus x1, it's the same as doing y1 minus y2 over x1 minus x2. It's kind of the same thing. So common ratio means that this is geometric. And again, I see an n here. That means I have to know the number of terms in the series, which makes it a finite series. Okay, in this formula down here, there isn't an n. And there isn't an n because geometric, oh boy, because this one is an infinite series. Okay, meaning you're just adding things forever and ever and ever and ever with no end. Okay, just a quick reminder, we can only find an infinite series sum if the r value, if the multiplier is between -1 and 1. If it's greater than 1 or less than -1, there's no way to find the sum, okay? Because you're just getting too big forever and ever and ever, or too small forever and ever and ever. You're never converging in on a single number. So, next thing I want to talk to you about is summation notation, okay? So here's an example, and the first thing you should notice on the right here is that this is a linear representation, which tells me that it's going to be arithmetic, okay? These numbers here tell me the term numbers. So for example, what this is telling me is the term number starts at 1, T1, T of 2, T of 3, until I get to T of 10. So if I want to know what the actual terms are, I would be plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in for K. So 5 times 1 is 5, minus 1 is 4. Same thing, T of 2 is 9, T of 10 is 49, okay? So summation notation here represents 4 plus 9 plus ... plus 49, this sum, okay? And again, because it's arithmetic, and of course it's finite, I can use this formula right here. So the sum of 10 terms. Now, how do I know that there are 10 terms? If I listed the terms 1 through 10, there would be 10 of them. Anytime this bottom number is a 1, it makes your life really easy because this number is telling you how many terms there are, okay? In the next example, we'll talk about what if that's not equal to 1. So, n, number of terms, we just said is 10. The first term plus the last term divided by 2. And when we do that, let's see, 5 times 53, we get 265 is the sum of this series represented by summation notation. Okay? Well, what about this one? Summation notation again. This time you should notice, well, wait a minute, this is an exponential equation. So we are looking for, actually, I'm going to get rid of that. It doesn't matter. We could work with it either way. But this is going to make our example make a little more sense and be a little more consistent to what we've seen. Okay, so because this is an exponential equation for the rule, that tells me it's geometric. And again, because it goes from 0 to 4, 0, 1, 2, 3, 4, I know it's a finite series. If this had an infinity sign above, it would be going on forever and ever. And I actually couldn't find the sum of it. I could still write it in summation notation. I can't find the sum of it because this r value doesn't fit in between -1 and 1. So again, what this represents is k of 0 is what happens when you plug in 0 for k. So 4 to the 0 power is 1. 3 times 1 is just 3. K to the first, when I plug in a 1, I get 12, all the way down to k to the fourth, which is 3 times 4 to the fourth, times 4 to the fourth, 768. So I could represent it this way. But in one of the videos I posted for you, Mr. Havens talked about, let's make this easier on ourselves by changing this to 1. So all I did was I added 1 to the bottom. 0 to 1, I added 1. So of course, that means I'm going to add 1 to the top. Now, to compensate for that, I still want my first term. Okay, so I know this is kind of confusing, but k of 0 is 3. I still want my first term to be equal to 3. So if I want my first term to be equal to 3, I have to compensate for the fact that I added 1 to this, so I have to subtract 1 in my formula. Okay, again, now if I plug 1 in for k, 4 to the 0, that's 1, times 3 is 3, this is still accurate. Okay, and it doesn't really matter that I'm calling the terms different things as long as I have the right terms. Because again, in the long run, and then in this case, when I plug in a 5 for k, I will get 768. So in the long run, both of these series represent 3 plus 12 plus ... plus 768. And that's really what we're trying to find the sum of. So we just wrote it in a way that might be easier for us to understand. Okay, when we come over here to the formula, the sum of, again, when this is 1, this number 5 tells me there are 5 different terms. 1, 2, 3, 4, 5. Same thing here though, 0, 1, 2, 3, 4, that's also 5 terms. Okay, so I'm going to write my first term. Again, either way, my first term in the series is 3. Don't get hung up on the fact we called that k of 0, k of 1. Let's just say it's the first term in the series is 3 times the ratio. Well, the ratio is found here or here in the formula, so 4 to the nth power. Again, n just represents how many terms. There are 5 terms no matter which of these two you're using. Minus 1 over 4 minus 1. Okay, we throw that in our calculator. 3 times 4 to the 5th minus 1 divided by 3, and we get 1,023. Okay, and that should work no matter which way you did it, because again, we're just talking about using this as our first term. Our ratio, common ratio is still the same. Okay. The last thing I want to do for you in this video is to go through these 4 closure problems, and these are not exactly the same thing that you see in closure, but they match up exactly with what you're seeing in the closure. So I'm just kind of pulling some stuff that I think will help you. So this one is example 1. It says find the sum. So of course, again, we have to figure out, we are doing what each time? We're subtracting 7, okay? And we never just want to look at the first two, because of course you could find a sum or difference between the first two. We want to make sure that that sum or difference is consistent, and checking 2 steps is enough for what we're doing this year, okay? So because it's a common difference, we're going to use the arithmetic finite series, okay? And we know it's finite because it has an ending here. So the sum of, I don't know how many terms it is. So sum of some number of terms is, I don't know the n. We'll figure that out in a second. But I do know the first term, and I know the last term, and of course I can divide by 2. So how do I figure out the number of terms? Well, I'm going to write a rule. And again, I think it's easiest to use first term form. So here's the first term. What's happening after that? We're subtracting 7. And when I use first term form, I always want to use n minus 1. And again, that's because if I'm thinking, what's the first term? 1 minus 1 is 0. 0 times 7 is 0. 27 minus 0 is 27. Okay, so my first term should be 27. This makes it match. Now, negative 50 is some term in my series, and I want to figure out which term it is. So I'm going to plug it in for t of n. I'm going to subtract 27, then divide by negative 7, and then add 1. And I'm getting that n is 12. So that means there are 12 terms in this series. I don't need to write every single one out by following the pattern. I can just solve algebraically. So again, number of terms times first plus last divided by 2. So I've got, let's see, 6 times 27 minus 50, and I get negative 138. Now, for some reason, students become a little bit uncomfortable when the sum is negative. But there's no problem with a sum being negative. If you add up more negatives than positives, or higher negatives, bigger negatives than there are positives, it's okay for your sum to be a negative number. Okay, example 2. This is the famous rebound ratio that you did in Algebra 1. You dropped the ball, or you threw the ball in the air, and you saw, well, if it bounces this many times, what the height is. Now, what's new this year in Algebra 2 is actually figuring out the total distance, or summing the distance, finding a series of the total distance that the ball travels after a certain amount of bounces. So, from the ground, a ball is thrown 14 feet into the air. The rebound ratio is 0.56. How far will it have traveled after 4 bounces? Okay, well, first of all, it's telling me a ratio, and so of course that's going to give me geometric pattern or an exponential pattern. Okay, remember, when I throw the ball up into the air 14 feet, it has to come back down, so that's going to be a total of 28 feet. So 28 feet is really my first term here. Okay, it tells me 4 bounces, so that's finite. So I want to use this formula. So the sum of 4 bounces is equal to my first term, 28, times the rebound ratio, 0.56, raised to the nth power, 4 bounces, minus 1, all over my rebound ratio, minus 1. Again, just going to use, I like my fraction button, alpha y equals enter for these problems. It just makes it harder to make a mistake. Not to say I've never made them, but it really helps. Okay, and I'm getting, okay, too many parentheses. Oh, I see. Just as I say, we can't make any mistakes. I got a negative number. I knew that didn't make any sense. In this case, you can't travel a distance that's negative. I put a minus or a multiplication instead of a minus. That looks a lot better. So I'm going to round. It's approximately 57.38 feet is the distance that the ball would travel if we're going 4 bounces. Now, this is another good example of when we would actually want to potentially use this formula, only if I said, hey, let's let the ball bounce forever. How far is it going to actually travel? So the sum, when it's bouncing forever and ever and ever, I don't care about 4 bounces, it just keeps going, is again, the first term, which is 28 feet, again, up 14, down 14, that's where we get the 28, our rebound ratio 0.56, and minus 1. Okay, so let's see what happens when we do this. 0.56 minus 1, and we're getting a negative, which doesn't make any sense. I gotta double check my formula, and in the meantime, I'll come back to this at the end, or I'll post in the lesson. I'm not going to stop the video. I have a feeling these two are reversed. I gotta double check, okay? But plugging our numbers into the formula, and it does make sense that we can use the infinite series formula because this rebound ratio is in between -1 and 1. And again, I'm going to come back to this or post in Google Classroom why that became negative, okay? But I'm not going to start all over for that. Next, number 3, write the series using summation notation. Summation notation is that sigma notation that we were talking about. Same thing. I've got 2 examples here. This one, what's happening from term to term is that we are adding 4. So again, when we're adding, we know it's arithmetic. And notice this just goes on and on and on forever. So if I'm going to represent this using summation notation, I recommend that you use 1 as your starting value. You could use any number you wanted, but really I recommend using 1. And because it's going forever, we can go to infinity, and now we just have to write the rule. Okay, well, I'm going to use first term form because I started with the first term down here. So 4, and then we're adding 4 each time. There's my sigma notation. If you really want to start with 0, k equals 0, then you have to go backwards and find the 0th term that's not even there, okay? Or you could certainly simplify that, okay? And we could say, oops, this should be k, because that's k. Same thing here, okay? Because my 0th term would be 0 in this case. Both of those will give you the same thing. Now, can we actually evaluate the sum? The answer is no, because it just keeps going on and on and on forever, but we can represent this series in summation notation, okay? Either one of those is fine. In part B, this time we're adding 2, but then, that's not adding 2. So we are actually multiplying by 3 every single time in order to get to this. So again, I highly recommend that you just start with 1, and then we got to figure out where we end. Which term is this? So 1 is t of 1, 3 is t of 2, 9 is t of 3, but what is this t of? I'm going to put n here for now. I've got to write a rule for what's going on here. Again, I'm going to use the first term formula. What's my first term? It's 1. What's happening each time? I'm multiplying by 3. And so because it's first term, I'm using k minus 1. So 6,561 is equal to 1 times 3 to the k minus 1. Now, we would divide both sides by whatever this number is. When we divide by 1, that's really easy. And then I would use a little bit of guess and check, okay? Because I know if this is a term in the sequence, it has to match up perfectly here. So I'm going to guess 3 to some power gives me this. And it is 3 to the 8th power. Gives me 6,561. So I am solving by using a common base. When your bases are common, you can just say, hey, the exponents have to be the same, which makes k equal to 9. That's what this is. This is the 9th term, okay? So here I go. This is how I write it. And again, because this is a finite sequence, it ends, sorry, a finite series, it ends, it has one final term, I can actually use this formula to help me find the sum, okay? But this just asked me to rewrite it in summation notation. Very last example that I want to do for you. Example number 4 says, consider the series, okay? So summation notation from n equals 0 to infinity of 5 times negative 3/4 to the nth power. First of all, what type of series is it? Well, because this is an exponential rule, we know that it is a geometric series. Okay? And of course, because it goes to infinity, it's actually infinite geometric series. Probably should rewrite that the other way. Okay? Now, this isn't asking if it's a finite series or not. We just said it's an infinite series because it goes to infinity. But does it have a finite sum? Can we find the sum of this series? Okay? And the answer comes from, well, what's the ratio? Is it between -1 and 1? And the answer is yes. Since our ratio is between -1 and 1, then it is a finite sum, yes. Because the ratio is between -1 and 1, we can find the sum. So part C says if it's a finite sum, then let's find the sum. So S of n, the sum, is equal to the first term divided by the ratio minus 1. And again, I'm going to have to go back and double check this real quick. But I will get back to that maybe in a second really quick video, or I'll just type it into Google Classroom. Okay. And on top, how do I find the first term? Okay, well, that's n equals 0, so I probably should do this. I'm going to adjust n equals 1 and put infinity here, -3/4. Let me look at my notes. Okay. I'm going to stop here and I'm going to make sure that I get this right before I tell you one thing and then I have to retell you something. So I'm going to come back and I'm going to let you know in a very brief video about example 4, and I think it was the end of maybe example 2. Okay, so thank you for hanging with me.